circles. Circles. Syllabus from class 10, board CBSE. Board CBSE. Let's start now. In the class 9, you have studied that circle is just a collection of points placed in plane from a constant, forming a constant distance from fixed point P. I'll repeat. Circle, this is from class 9 definition. Circle is a collection of points placed around one fixed point at equidistance. These are all at equal distances. These points are all equal distances from point P. Now this fixed point P is called center. And the curve that forms is a circle, of course, when you join these points. And this distance from the point on circle to the fixed point P is radius, usually indicated by a small letter r. Now, definition of circle can also be defined in another way as locus of a point which moves in a plane such that the point moves at a constant distance from the center. Now look at my hand, forefinger, and I am placing my thumb on the board which forms my center of the circle. Now this fingertip that is moving like this, it's just defined like that, circle. Circle is a locus of a point which moves in a plane such that the point is moving at a constant distance from the center. This is again radius, and this is center, and so on and so forth. That is basic definition of circle. Now, when I take circle and a line and find out what the circle and line forms, I'll have three cases. Case 1, the line just could not be touching anywhere, or it could just be lying outside of the circle like this, or anywhere. The line could be anywhere. Now this line and circle are not, they form non-intersecting pair. Non-intersecting. Next, second case, I could have this same line intersecting, let's say somewhere around here. You can just take anywhere. This line, say this is x, say this is y. Say this is x and this is y. Now this line is intersecting the circle at 2 points. This line is not intersecting the circle, not at all intersecting. Center, center. But this line is intersecting the circle at 2 points, at say A and B. Now this line forms secant. It's called secant. A line which intersects the circle at 2 points is called secant. Case 3, you have case 3. Circle and a line just touching. Circle and a line is touching. And this is a line, say x, y. It's touching at just one single point. Though on the board it might appear as if the line is making contact at several points, but actually it's just at one point P. This line forms tangent to the circle. Tangent. Now how is tangent defined? Tangent is a line which touches or meets the circle at just one point. I'll repeat 3 cases again. I had taken a circle and a line. The first case had line lying outside of the circle, touching nowhere, just non-intersecting pair. And the second is a circle intersecting at 2 points, at A and B, forming This line was called a secant. A line which cuts the circle at 2 points is called secant, and a line which just touches at one single point is called a tangent. I'll paraphrase and draw the diagram here. The theorem 10.1 is given in terms of statement as the radius of a circle meeting the tangent is at right angles. Now this is a tangent, say xy, and let me indicate the center by letter O, and this is radius r, and this radius or the line which is dropped from point O onto the tangent, let me indicate at this point as P. I have to prove that, to prove OP is at right angles to the line xy, or OP is perpendicular to xy. Prove that OP is perpendicular to xy. So before we go any further, let me take one case here separately. I have two parallel lines, right? You know that this is the minimum distance between the two lines. If I am dropping a line from here onto this line, this is the least distance. If I am dropping a line from this point onto this line, anywhere apart from this point, the distance is going to increase like this. If I am dropping at this point, let's say this is D1. If I am dropping a line from this point again to here, let's say this is distance D2. So distance D1 is lesser than D2, is lesser than D3, so on. So it means that between two parallel lines, this is the least distance, which also means that this line is also perpendicular. Just by observation, you can say that this line, this particular line, is perpendicular to this line, say AB. So line PQ, let's say this line as PQ is perpendicular to AB. So that is basic concept involved here. Now I have to prove here OP is perpendicular to XY. So what I'll do is I'll take point Q on this line somewhere, and you can take anywhere except on P. You cannot take it on P because that is what I have to prove. If I take a point anywhere on the XY except here, except at point P, the distance is going to increase. Now let's see how many tangents can a circle have in different cases. This is circle. When the point is lying within the circle like this, how many tangents can we draw? How many? Not a one. Not a single tangent you can draw. 0 tangents. That is because tangent's definition is, the tangent is a line which meets the circle at one single point. So it has to meet one single point like this, just one single point. So when I draw a line from here, anywhere in any direction, it does not touch at one point, it is touching at 2 points. So how many tangents can a circle have? 0 in this case. Let's see how many tangents can a circle have when the point lies outside of the circle. Point is outside. How many tangents at maximum can you have? Just 2 tangents. If this is point P, and let me indicate this point as T1, the point of this point T1 is called point of contact. And this T2. Point of contact is the point of intersection of the radius or the line dropped from the center onto the tangent. That is point of contact, where the point of contact is point where tangent meets this tangent meets the line dropped from center. Drop from center. That is point of contact. Now, when point was lying within the circle, you had just no tangents that can be drawn. But when the point lies outside the circle, you will have two tangents that you can draw. But what happens when the point where you are drawing the tangent lies on the circle? Say this is the point. You can have just only one single tangent at one point. Now I have a question. If at one point a circle can have only one unique tangent, or that is just one tangent at one point can be drawn, so how many tangents can a circle have? Let's see now. How many tangents can a circle have? Circle, as I've defined before, is a locus of point which moves in plane such that its distance, the distance of these points, is a fixed distance from the center. If this is a center and this point moves around the center at a constant distance, then the distance is called r. There are infinite such points, and at one single point you have one tangent drawn like this. So therefore infinite is the answer. Infinite tangents.
No more spending your energy and money on coaching classes, or missing classes for rain, for rally, and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. So sit back comfortably in your home and watch Study Spectrum TV channel.
10.2. To prove that length of the tangents drawn from an external point are equal, I will draw the diagram. To prove that length of the tangents drawn from a point external to the circle are equal in length. Let me indicate this as point P. From this point I am drawing tangents. Now length of the tangent starts from the point of contact here to the external point. Again, the point of contact to the external point. Let me indicate the center with letter O, and let me join these 2 points. Now from the theorem 10.1, you know that line dropped from the center onto the tangent is at right angle. These are at right angles, and I indicate this point by T1 and this point, this point of contact, by T2. We have to prove that PT1 is equal to PT2. That is, these two tangents are equal in length when they are drawn from a point external to the circle. Before I tell you anything, and before I go ahead and prove it, I have to tell you the concept of similarity and congruence. Similarity and congruence. Similarity. Many times you heard saying two triangles are similar or two circles are similar, which means that the two circles or two triangles may or may not be of same size. Now in this case, the circles almost look like of similar size or almost same size. They are of almost same size, so they are similar. You can say that they are similar. Are they congruent? What's the difference between similarity and congruence? Congruent is nothing but all the dimensions of any given figure should be equal. When I'm drawing a triangle, all the sides A, B, C should be equal to another triangle having length A, B, C as its sides. Now here in similarity, you may or may not have objects of equal sizes, but the shapes should be same. Now all three circles are similar, but they are not congruent. Only these two circles are both similar and congruent, but this circle is similar to the other two. Similarly, when I am drawing a bigger triangle like this triangle is similar to these two triangles, but it is not. This triangle is not congruent to any of the two triangles drawn here, figure 1 or 2 here. But this triangle 1 and triangle 2, they are congruent. They are congruent as well as similar. So the conclusion is that a figure can be both congruent and similar, but not necessarily vice versa. A congruent figure need not be similar. Congruent figure is always similar figure, but similar figures cannot be, they cannot have congruence. They may not have congruence. So that is there. Now based on that concept, let me draw the line from O to P. Based on that concept, I'll derive. We have two triangles here, triangle OTP and triangle OT1P and triangle OT2P. So triangle OT1P and in triangle OT2P. OT1 and OT2 form radii of circle, so they will be of equal length. I'll write OT1 is equal to OT2. Now side OP is common to both the triangles. Side OP is common to both the triangles. So I'll write OP is equal to OP. Now what is the left out side? This PT1 will be, we have to prove that, PT1 is equal to PT2. Now let's take a look at the angles of the triangles. In triangle OT1P, angle OT1P is right at right angles, that is 90 degrees. Now its corresponding angle in the triangle OT2P is also right angle at right angles, that is 90 degrees. And this angle is bisected by a line OP, so this angle will also be equal. Now this is 90 degrees and this will be some, say, x. If this entire is 2x, and this will also be x. So 90 plus x, and here also there is 90 plus x in both the triangles. So shouldn't this angle be same? T1 OP, T2 OP, both angles will be equal. That is because we know that sum of all the angles in a triangle is 180 degrees. So I'll repeat this again. This is at right angles. This angle is also at right angles. And I've drawn OP here, which bisects this entire angle 2x. It bisects entire angle 2x, which means that half the angle goes here and half the angle comes here. Half is xx. So therefore, this is 90 degree plus x. So I'll write here, in triangle OT1P, 90 plus x plus T1OP. T1OP is equal to 180 degrees. So in triangle OT2P, in triangle OT2P, you have 90 plus x plus this angle. 90 plus x plus, that is, this angle is T2OT. So therefore, I can say from here you have T1 OP is equal to 180 minus, I am shifting these two terms to the right hand side, they become 90 minus x. This is equal to 90 minus x. That is angle T1 OP. Here angle T2 OP, T2 OP will be equal to 180 minus 90 minus x. This is equal to 90 minus x. So 90 minus x and 90 minus x, they are equal in magnitude. So I can equate T1 OP P equal to T2 OP. T1 OP is equal to T2 OP. Now T1 OP is equal to T2 OP. Firstly, I had OT1P at right angles and then OT2P at right angles. That is, corresponding angles of these two triangles are equal and they are 90 degrees. Also, corresponding angles at bisected part are also equal. The remaining part, I proved that the remaining angle, I proved that they are also equal. So which means that all the three angles of both the triangles are equal in magnitude, which means that these two triangles are congruent. So therefore I conclude that this side will be equal to the other side. That is, PT1 will be equal to P2 because in congruent triangles you will have all the angles as well as sides having equal magnitude. So therefore PT1 is equal to PT2. I'll repeat this. The concept of congruent here is, you have triangles, you should and must have all the sides, all the corresponding sides of equal magnitude. If this is x, this will also be x. If this is y, this will also be y. If this is z, this will also be z. Similarly, you will have angles. What I did in this case was, I proved that all the angles, all the corresponding angles in two triangles are equal. All the angles in the corresponding triangles, the corresponding angles in two triangles, the corresponding angles in these two triangles, that is triangle OT1P and triangle OT2P, OT1P and OT2P. I have proved that corresponding angles in these two triangles are equal. So therefore corresponding sides should also be equal. Therefore I conclude that PT1 is equal to PT2 because these two sides OT1 and OT2 are radii, so they will be equal, and OP is a common side which is common to both the triangles, which will be equal in both the cases. So therefore this is equal to PT1 is equal to PT2. Hence we proved that two tangents drawn from a point external to the circle P are equal in magnitude. PT1 is equal to PT2.